In this video, we're going to talk about the relationship between Ka, Kb, and pH. So in the first problem that we're going to do, we're going to look at determining the pH of a solution of a weak acid where we know the initial concentration and we know the Ka value for it. Whenever we're approaching a problem like this, what we need to do is set up a Rice table, which shows the reaction, the initial amounts, the change, and the equilibrium concentration. So when we do one of these problems, we're going to assume that initially all of it remains in the unionized form and that we have no ionized products. So over the time that it gets put in the solution, you're going to have the acid dissociate to some percentage or some portion. That change, the amount that dissociates, is going to be equal to the amount of hydrogen ions formed as well as the conjugate base formed because it's a 1-to-1-to-1 reaction. So at equilibrium, we could say that the concentration of our weak acid remaining in solution is going to be 0.1 minus X, and that our concentrations of hydrogen ion and the conjugate base would both be represented as X. So when we plug this into a Ka expression, we see that we get X squared in the numerator because the numerator represents the concentrations of the products multiplied by each other over the reactant concentration. So since we have a value of 5.0 times 10 to the negative 6th, what we can then do is simplify this because any weak acid with a Ka less than 10 to the negative 4th, we can actually ignore the loss of the unionized acid, which makes the equation become quite a bit simpler. It goes from being a quadratic expression to something where you just have to take the square root. So solving for X, we find that, which is equal to our hydrogen ion concentration, which we can use to calculate the pH, X is going to be equal to 7.1 times 10 to the negative 4th. And using that value, pH is a negative log of that value, we'd see that the pH would be 3.2. In the next example, we're going to look at a basic solution because we've usually focused on the acids in class. Determine the pH of a 0.2 molar weak base where the pH is 10.2. And we're going to determine the Kb. So the reaction that we have here is that the base is going to absorb a hydrogen from water. We don't need to show water in this expression because it's a pure liquid and it's not going to be involved in the equilibrium expression. Forms the conjugate acid and the hydroxide ion. We assume that all of the base hasn't performed that process yet at first, and that we have no products and it's all reactant. Now, different from the other problem is we already know the pH. And if we know the pH, we can calculate our hydrogen ion concentration and our hydroxide ion concentrations from that. So we take the POH, we subtract the pH from 14, and we get that our POH is equal to 3.8. Solving for the hydroxide ion concentration, which is one of the products that we're going to be looking at equilibrium to determine our K expression, the hydroxide ion is equal to 10 to the negative POH, 10 to the negative 3.8, which is 1.6 times 10 to the negative 4th. So filling out the rest of this chart, our change is that the base, it's going to lose 1.6 times 10 to the negative 4th. The conjugate acid is going to go up by that value, and our hydroxide will go up by that value as well. When you subtract this value from 0.2, because it's a weak base, it actually has no impact on that. If you line it up and do your sig fig calculation, you'll see that it has zero impact on this. So at equilibrium, our concentrations are as follows: 0.2, 1.6 times 10 to the negative 4th, and 1.6 times 10 to the negative 4th, respectively. When we plug that into our Kb, or our K expression for a base, we see that we get a value of 1.3 times 10 to the negative 7. So this is how we can relate pH as well as our K expressions for acids and bases.